So let's wrap up chapter 18. We have a couple of additional slides to discuss a different type of mechanism. Thus far, we were mostly concerned with electrophilic aromatic substitution reactions, and now we're switching mechanistically as we are dealing with nucleophiles for the reaction conditions. So benzene is now being attacked by a nucleophile. We need to understand what it means to read these conditions. Here, OH minus is the nucleophile, and Br minus is the leaving group. Okay, so we need to utilize our foundational skills on how to use our mechanistic insight. What constitutes a nucleophile? What constitutes an electrophile? And how do we use the curved arrows to trace these electrons in the mechanism? You may remember in Orgo 1 when you studied many different conditions for nucleophilic substitution reactions. And I want to caution you here because we cannot simply formulate a mechanism in which we discern from Na plus OH minus that we have now our O minus and then a bond to hydrogen. So here's the hydroxide ion, and that we would simply use one of the free electron pairs and do a substitution reaction like you learned in Orgo 1 and just kick out that bromine. Okay. I'm going to tell you that that is incorrect. I'm going to pause here. Why would that not be a suitable mechanism? Okay, once we analyze the structure, the main difference to the reactions in Orgo 1 is that here we have an sp2 hybridized carbon. We cannot do a nucleophilic substitution reaction as drawn here. So this is no good, and let me just cross all of this out. Okay, so this is not the mechanism that is occurring, and we have data to support that. Nonetheless, we are able to replace the bromine with a hydroxyl group. Let's look at the details. What's required for a nucleophilic aromatic substitution reaction? So there are three requirements that we need to utilize here. We also abbreviate this as SNAR. The benzene ring, for one, must have a very strong electron withdrawing group. Remember how I stressed to have detailed knowledge as to the bonding patterns, and we had learned that a nitro group is an excellent electron withdrawing group. What this does is it decreases the electron density in the ring, which means a nucleophile will be attracted to the ring and a reaction can occur. The ring also must possess a good leaving group, for example, a halide, and the leaving group must be positioned ortho or para. What happens if the electron withdrawing group is in the meta position? No reaction is observed. Okay, and it has to do with the electron withdrawing group. When it is in the meta position, it's unable to stabilize the intermediate. The intermediate here has a specific name. This is the Meisenheimer Complex. Remember how we had discussed electrophilic aromatic substitution reactions, and we could draw 3 or more resonance forms for that double allylic cation for the sigma complex. If we have a negative charge that is being pumped into the aromatic ring, we now call it the Meisenheimer complex. Here's the mechanism. We see our hydroxyl group. It will attack in this position, and then the electron density can be located in this position here. And we can swoosh this around, so then we do another kind of allylic movement. This is something that you were actually introduced to at the very beginning, definitely chapters 1, 2, and 6. So as we formulate resonance structures, we can now locate the negative charge here. If we look at the ortho anion here, again, we could go back to this. We could actually go from here and pump it into the nitro group, Or we draw 3 curved arrows to get to this 4th structure. And because of the presence of the nitro group, either in the ortho or para position, the electrons are set up such that you can form more resonance forms for this Meisenheimer complex. And then, sort of like a domino effect, all of this can come back. This can be written in more than one step, making a double bond to nitrogen. It can only have 4 bonds, so we'll have to move this into the ring. This then collapses, or this then reestablishes the double bond here, and we kick out Cl- in the structure. But if you do not understand how to draw this, then you will struggle to formulate a mechanism for this. What else do we need to understand? So in these nucleophilic aromatic substitution reactions, when we have a substitute phenol that is deprotonated under basic hydroxide conditions, okay? And so basically we need to add a second step. You may see this shown either with 2 arrows or both conditions are drawn just with 1 arrow and summarized. Okay, but this is some basic acid-base chemistry. So OH- attacks here. Remember, Meisenheimer complex can push the electron density all the way here, and then like a domino, it comes back and it kicks out the bromine. And immediately after the OH is attached, it will be deprotonated under basic conditions, and you form the hydroxide anion as shown here. Then we're basically introducing a net H plus with an acidic workup, and out comes the hydroxyl group. Again, I encourage you to practice this with so many homeworks that are available in the textbook. Moving on, there is another set of reaction conditions available. I try to color code this a little bit. So in 1814, what we're dealing with is a different type of mechanism. We first eliminate the leaving group, and then we're adding the nucleophilic component. So we will not have a nucleophilic substitution if the ring doesn't have a strong electron withdrawing group. Okay, so if we were just to use basic conditions and heat this up, this would not be sufficient to get a reaction. But if we're using more extreme conditions, so here you see sodium hydroxide and heat, sodium hydroxide and really high heat, we can persuade the reaction. These are much more extreme conditions, and we will accomplish the substitution of the chlorine in here, followed by an acidic workup. Additional information is summarized on this slide. We have even better outcomes when we don't require high temperatures. So we're using far more or much stronger reagents. What we see here is sodium amide in liquid ammonia. That's what the L stands for. Ammonia is a gas. If we run the temperature at low enough, if the reactions run at low enough temperature, we can dissolve the sodium amide, which is a very, very powerful base. You may remember from the alkyne chapter in Orgo 1, but it can also, in this case, be a very strong nucleophile. And before we go further, let me just switch over to my ChemDraw slide. So as we're looking at these conditions, remember this is sodium amide. Let me just spell this out, sodium amide. I could even use my program and just convert this. So here we have it, right? But again, this is a mixture of 2 ions. We need to be able to draw what sodium amide looks like. Here's my nitrogen. And basically, we have to realize that there are 2 free electron pairs on that nitrogen. Let me draw these in. And with these 2 electron pairs comes a negative charge. If you're having trouble with this, you really need to go back to chapters 1 and 2 and practice the formulation of ions and using good Lewis structures. So here we are. Let me increase the size a little bit. And let me switch this. I would like to scale everything a little bit higher. Okay, so here we are. We have our 2 free electron pairs here, and they can now act as a base or as a nucleophile, depending on what the substrate is. Okay, maybe I'll copy this over to the slide. So remember that this is an important understanding on the molecular level for the conditions here. Okay, and then sodium is your counter ion. All right, so what's going on? What's the mechanism here? What's happening? It turns out when we run this reaction, not just with chlorobenzene, but have another substituent in the structure, we obtain 2 products, which gives us mechanistic insight. We therefore need to discuss a little bit what is going on. As we're looking at the structure, we have to assess the regiochemical outcome. So why is it that the nitrogen would end up here or here? So obviously this is acting as a nucleophile and displacing the chlorine in the same position, but it can also end up 1 over. So what is going on in here? Well, we need to eliminate one of the hydrogens first. So if we are thinking about that there's a hydrogen here, and there's some symmetry, but as it is written here. So if we're eliminating HCl first, we can then see how the nitrogen could end up in this position. Chemists have run isotopically labeled experiments to get mechanistic insight. And here is an asterisk, and then we see it here and here. And because we have isotopically labeled the starting material, the substrate, it's clear that the substitution is now occurring at 2 different carbon atoms. This can only be due to the formation of what is now referred to as a benzyne intermediate, and that's a really unusual structure. Here you see benzyne drawn, and here is a triple bond. This might be very confusing because how can we have a triple bond in a cyclic structure where there are only 6 atoms present? It would distort the bond angle. We know that a triple bond would like to be sp hybridized with a 180-degree bonding pattern. So it should be linear, and we can't really accomplish that in a 6-membered ring. Another way of thinking about this is that even though it is drawn with this triple bond that makes a chemist kind of cringe, we can think of this having a diradical character. So there is a radical here, so big dot, and a radical here, and that they would sit in different types of orbitals. That's another theory of thinking of what this benzyne atom is. And as we're then looking at this, we can now understand when we have this benzyne intermediate that, this wants to be broken apart. So again, here's the triple bond. This is how this textbook phrases this or describes it. This is the nucleophile attacking either here and then locating the negative charge in this position. And then the outcome is, upon protonation, this is run in liquid ammonia, we would get this product. If now the nucleophile attacks in this position, placing the negative charge here, then protonation would lead to this product. Remember how this is now labeled. So here is our asterisk, not to be confused with the radical or diradical theory I indicated before. This is the isotopically labeled carbon. We now see that it has to go through an unusual intermediate, so the benzene is formulated like this, and this is now described as an elimination and then addition mechanism. All right, so again, in more detail, we have a proton transfer under strongly basic conditions. Here there's hydroxide, it forms this anion, then we can eliminate the leaving group, we get the benzene structure, and then we would have the hydroxyl group attack here. In this case, there's nothing labeled, there's no other second substituent, so we just localize the negative charge here, and then protonation will lead to this. We have other evidence for the formation of these strange benzene intermediates. Again, I want to cringe here. It does exist. We have different trapping experiments that confirm the presence of something like this, even if you think there's a diradical character, that there's some orbital overlap. So anyway, we're drawing this triple bond in the six-membered ring. Remember how we discussed in chapter 16 Diels-Alder reactions? Diels-Alder reactions were 4 plus 2. So this would be your 4-electron system, and this would be your 2-electron system. And we would form, remember, these are always going to be cyclohexene derivatives, because we start over the triple bond. We have a second double bond in here. And we can trap this benzene intermediate by having a diene in the structure present, and this would be your cycloaddition product, your Diels-Alder product from the 4 plus 2 cycloaddition reaction, and you can practice this as well. Okay, here's another practice. You may want to pause here, think about it. I actually included this in one of the worksheets for the lecture material. Let me switch over to my ChemDraw. Again, we want to understand what do these conditions really mean. You need to analyze what is present. We have a leaving group. It's either abbreviated as LV or as LG, depending on which textbook you look at. We have one of the strongest electron withdrawing groups, so that should give you a hint what can happen here. Moreover, these two substituents are in a para position, so they have a para relationship. Do you know how to formulate a mechanism? Again, it's much better for your mastery if you can deduce the answer based on your mechanistic insight. Let me switch over to my ChemDraw. All right, so as we're looking at this here, we want to understand that CH3ONA is a source of CH3, and then we have O, and we need to show our electrons. And we now have a negative charge on oxygen, which makes it a good nucleophile. Let me drag this a little bit out. Oh no, I want an oxygen there, so... And let's scale this a little bit. All right, here we are. We have a good nucleophile. It will help you to spell out or to draw out in detail the nitro group, because then you can use your curved arrow formalism. Let me see, which would mean you first attack. I think I grabbed the wrong arrow. You need to draw a full curved arrow. Start here, move over here, and then you can delocalize in one step, once you draw this out, all the way to the oxygen, and then this will collapse back and kick out the chlorine. So remember, our ability to draw good Lewis structures showing all bonding and non-bonding electrons will help us understand this. So you have the Na plus counter ion that doesn't do anything in the mechanism. All right, to sum up this chapter, which was very heavy on mechanistic information, we need to be able to identify the mechanism. The majority of reactions in this chapter are electrophilic aromatic substitution reactions. So you need to understand what's an electrophile, what's a nucleophile, need to be able to read the reagents over the arrow to discern that basic aspect. If you have an electrophile, it will be electrophilic aromatic substitution. If you have a nucleophile, you need to ask another question. Are all three criteria satisfied for nucleophilic aromatic substitution reaction? If yes, you will have SNAR. If not, remember we had to say orthopara position of a strong electron withdrawing group. If not, you may still have a reaction. It would then proceed via an elimination addition reaction, and you can practice with Skill Builder 18.7. Couple more slides. Here are the vast majority of reactions, 1 through 6. Remember how we started out reading the reaction conditions, identifying where E plus is. So what's E plus? What are the conditions in here? And then we also learned that some of these function groups can be further converted from a nitro group to an amino group. If we have the benzylic position here, we can take advantage of a radical bromination reaction in the benzylic position. We can take advantage of oxidative conditions to get to a carboxylic acid, or after a Friedel-Crafts alkylation that is shown here, we can reduce the carbonyl group and replace it with 2 hydrogens. A much better way with much more control compared to the Friedel-Crafts alkylation reaction where we discussed some of the drawbacks. And on the last slide, again, those other possible mechanistic approaches for depending on what the conditions are. So nucleophilic aromatic substitution, SNAR, presence of a strong electron withdrawing group in the ortho or para position, strongly basic conditions, some heat is needed. We need to follow up with a quench because the alkoxide ion forms initially, or an elimination addition reaction, much stronger conditions, much more extreme conditions, much higher temperatures compared to 70 degree here only, or having liquid ammonia. This is typically at low temperatures to condense the ammonia in which you dissolve the sodium amide, and we had looked at the isotopic labeling process here. This concludes this chapter. Again, if you're still struggling with mechanistic information, please go to chapter 6.7 through 6.12 and practice your foundational skills there. It will be a good investment for subsequent chapters to come, where many more transformations are happening, and mechanistic insight will make our lives much easier.